Hi, I am Sanjay Patel. In this video, we are going to discuss algebra of convergent and divergent series. Means if you have two series which are convergent, what can you say about their sum and difference and multiplication by some constant and so on. So let us begin with the first one. The first result, if sigma an and sigma bn are convergent series, then prove that sigma an plus or minus bn is also convergent. Okay. So let us prove this. First of all, let us recall that to prove a series is convergent, we should show that the limit of its partial sum exists and it is some, say, finite real number. Okay. So here we have two series. So we'll define the partial sums for each of these series first of all. So consider this way. Suppose the partial sum for the sigma an is given by, say, Sn, which is nothing but a1 plus a2 plus a3 up to an. So this is the sum of the first n terms of the series sigma an. And we also define the partial sum of the second series sigma bn, that is b1 plus b2 plus b3, sum of the first n terms of sigma bn. Okay. As both the series are convergent, since sigma an is convergent, we can say limit n tends to infinity Sn is equal to S exists. And similarly, as sigma bn is also convergent, implies we can say the limit of the partial sums of sigma bn, that is n tends to infinity of Tn, this also exists and it is equal to some real number, say T. Okay, this also exists. Okay. Now we want to prove that this sigma an plus bn and sigma an minus bn are also convergent. Okay. So what we can write here is just it's a partial sum of this series for sigma an plus bn. So I am writing this way, and let us call it say un. Say the sum of the first n terms of sigma an plus bn, this series, similarly you can prove for minus also, is given by, say, un is equal to, say, a1 plus b1, okay, plus a2 plus b2 plus and so on plus an plus bn. This is the sum of the first n terms of this series. Okay. And this we can rewrite as a1 plus a2 plus a3 up to an by simplifying this, and b1 plus b2 up to bn. Okay. So in this case, what is the first bracket? The first bracket is nothing but this Sn, and second bracket is Tn. So I can write this as Sn plus Tn. Okay. So what we have proved is un is equal to Sn plus Tn, where un is the sum of the first n terms, of the series sigma an plus bn. Now if I take the limit of un, that is the sum of the first n terms of an plus bn, sigma an plus bn, then that means this is equal to limit n tends to infinity of Sn plus Tn. and this we can write as limit n tends to infinity of Sn plus limit n tends to infinity of Tn. Both these limits exist, so we can use these working rules of limit of sequences. And both of these limit are S and T respectively, which is given in these two statements because of 1 and 2. Okay. So what we have proved is limit of un is S plus T. Since S and T both are real numbers, so I can say this is also some finite real number. This is some finite real number. So limit of un exists means limit of the partial sum sequence of sigma n plus bn exists, and therefore by definition sigma an plus bn is convergent. So the conclusion is therefore sigma an plus bn is convergent. Similarly, we can prove that sigma an minus bn is convergent just by keeping minus sign. Let us go to the next result. It is also very simple. If sigma an is convergent, if sigma an is convergent and say C belongs to R is some constant, then prove that sigma C into n equal to 1 to infinity is also convergent. The proof is very simple here. So first we start this way. We want to prove that this series sigma C into an is convergent. First of all, for the sigma an, the partial sum, that is the sum of the first n terms of sigma an, is given by Sn is equal to a1 plus a2 plus a3 up to an. Okay. Now, as sigma an is convergent, we can say that limit n tends to infinity of the partial sum Sn exists. This limit exists and is equal to some finite real number, say S. So this limit exists. Okay. Now we want to prove that sigma C into an is also convergent. And for that, let us consider, let say Tn is equal to the sum of the first n terms of the series sigma C into an. So what is this series actually? This series is C into a1 plus C into a2 plus C into a3 and so on. So I can write this is equal to say C into a1, okay, plus C into a2 plus and so on plus C into an. These are some of the first n terms of this series which we are denoting by Tn. This we can write as C times a1 plus a2 up to an. But this sum is nothing but Sn. So we can write C into Sn. So what I have proved is Tn is equal to C into Sn for every n belongs to n. Now taking limit here in this both the sides, what we get is this. Therefore, limit as n tends to infinity of Tn is equal to limit n tends to infinity of C into Sn. This we can write using the working rules because limit of Sn exists. So this is equal to C times limit n tends to infinity of Sn. Correct? Constant you can take as outside of this limit sign, and limit of Sn is given as in result number 1 is small s. So C into S because of result number 1. And this is also some real number. C is a real number and S is also a real number. So this is also some finite real number. That means I can say the limit of Tn as n tends to infinity exists. This limit exists. And therefore, Therefore, I can say sigma C into an is convergent series. And not only that, we can also say what is the sum of the sigma C into n. The sum is C into S. And S is the sum of the series sigma an. Okay. So we can note one thing from this two theorems. If sigma an is convergent from theorem 1, we can say sigma an, okay, sigma an plus sigma bn is equal to sigma an plus bn. Okay, and if it is minus, then we can write minus here also, provided both the series are convergent. Provided both are convergent. Okay, means if sigma an is convergent, sigma bn is convergent, then the sum of sigma an plus or minus bn we can write like this. Okay, and secondly, we can also write sigma c into an is equal to c times sigma an for any real number c. Okay, again, if sigma an is convergent. If sigma n is convergent. And using the theorem 1 and 2, we can say that if sigma n and sigma bn are convergent, then any linear combination of a and bn is also convergent. Let us discuss some corollaries from theorem 1 and 2. So first corollary, it says if sigma an plus or minus bn is convergent, let us write only plus, sigma an plus bn is convergent, and sigma bn is convergent, and sigma bn is convergent. If you know that one of these two series, sigma n or sigma bn, is also convergent, then prove that sigma an is also convergent. What we have proved in the main theorems is if sigma n and sigma bn are convergent, then sigma n plus bn is convergent. The other way, if sigma n plus bn is convergent, and if you know one of the series, either an or bn is convergent, then the remaining series is also convergent. That is the aim of this result. So let us prove. It is very, very simple. Okay. What do we have here is sigma an plus bn. This is one series. This is convergent, and sigma bn is convergent. Okay, sigma bn is convergent. We can treat these two as two different series. So this is one series, a pn. This is qn. If sigma pn and sigma qn is convergent, then from the first theorem we can say their addition and subtraction both are convergent. So this implies sigma an plus bn minus bn is also convergent. And that means nothing but sigma an is convergent. Sigma an is convergent. So it is proved. Very, very easy. Now another corollary, number 2. Say corollary number 2 is this. If sigma an plus or minus bn, let me write only for plus sign. If sigma an plus bn is divergent, if this series is divergent, and say one of the series, either an or bn, is convergent, and sigma, say bn, is convergent. Remember that it is a different thing. Sigma an plus bn is divergent and sigma bn is convergent. Then prove that sigma an must be divergent. This is also divergent. Okay. How to prove this? Again, the proof is very simple, follows from the theorem 1. We have sigma an plus bn is divergent, that is given, and sigma bn is convergent, that is given. Okay. What is our aim is to show that sigma an is divergent. So suppose if possible, let us write this way. This will assume to a contrary. Suppose if possible, sigma an is convergent. Okay. But we are also given that sigma bn is convergent. Okay. So also we have sigma bn is convergent. It is given in the hypothesis. Okay. By hypothesis. And therefore, we can say that sum is convergent. Sigma n is convergent, sigma bn is convergent. Then from theorem 1, sigma an plus bn is also convergent. But this is a contradiction to the given hypothesis that sigma n plus bn is divergent. So we can say a contradiction to sigma an plus bn is divergent. So contradiction to sigma an plus bn is divergent. So therefore our supposition, this thing is wrong. So what is proved? Hence we can say that sigma an is not convergent, means is divergent. Okay, so because our supposition is wrong. Fine. So this we can think of if two series are convergent, one of the series is divergent, and so on. Now what happens if two series are divergent? Let us discuss something say extra, like say suppose I have two series, so sigma an is convergent, or let me say is divergent, and sigma bn is also divergent. Sigma bn is also divergent. What can you say about the sum? Will it be convergent or divergent? Sum or difference? What about this? Is it convergent or divergent? What? Okay. We'll see that nothing can be said actually, because if I take two series, say one series sigma an is equal to say sigma n, other series sigma bn is equal to sigma minus n. Sigma n means 1 plus 2 plus 3 up to infinity. Sigma minus n means minus 1, minus 2, minus 3, minus 4, and so on. Okay. So these two series we know both are divergent. But the sum, if you find, say sigma an plus bn, if you add all the terms, then all the terms will be 0. Okay, because an is n and bn is minus n. So an plus bn is n minus n is equal to 0. So for the sum of these two series, we are getting the answer 0. It is convergent in this case. This is convergent series. So therefore it is convergent. Okay. But if I consider another example, say if I take sigma an is equal to say sigma n square, okay, which is a divergent series, and sigma bn is equal to say sigma n, which is also divergent. This is divergent and this is also divergent. That we have discussed already. And therefore, if you find an plus bn, that is n square plus n, okay, find n plus bn, that is n square plus n, then that series sigma an plus bn is also divergent, is clear, because this will thus the partial sum of this series tends to infinity as n tends to infinity. So this tends to infinity. So it is divergent. What is the conclusion here is, if two series are divergent, then the sum can be convergent or it can be divergent. So nothing can be said in this case. Okay. Now finally, we would like to prove another important and useful result, and that is about convergent series or divergent series. It is applicable for both. That is, given a series, if you add some terms or if you remove some terms from the series, then its convergence will not be affected. So I'm writing this way: prove that first let me write in symbol. Prove that sigma n equal to 1 to infinity an is convergent if and only if sigma n is equal to m plus 1 to infinity an is convergent. What is the difference between these two? Here the series starts with a1, a2, a3 and so on, while the series here starts with am plus 1, am plus 2. So we have removed the first m terms. Okay. So if we remove first m terms from this, and if the series convergent, still remains convergent. Other way, suppose you are given that am plus 1, am plus 2, am plus 3 and so on is convergent series, then adding first few terms a1 to am, you will get this series, it is also convergent. So in other words, we can say that is addition. Let me write this way. If we add or say remove some finite terms, some finite number of terms from a series, from a given series, then its convergence remains unchanged. Means if it is original series is convergent, then if you add something or if you remove something from that, it remains the same. It is convergent and remains convergent, and if it is divergent, it remains divergent. So you can also write like this. Okay. 1 to infinity n is divergent if and only if m plus 1 to infinity n is divergent. So let us prove this. There are two parts here. It is if and only if. Let us prove. Okay. So first of all, let us write the partial sums for both the series. For sigma n, the partial sum is given by Sn is equal to a1 plus a2 plus a3 up to an. It is n equal to 1 to infinity. Okay, the sum of the first n terms of sigma n. And for sigma bn, or rather not sigma bn, but it is sigma an is equal to m plus 1 to infinity. For this series, the sum of the first n terms, you know what is this series? This series is actually am plus 1 plus am plus 2 plus am plus 3 and so on up to infinite terms. While this series is a1 plus a2 plus a3 and so on. So for this second series, the sum of the first n terms will write as Tn, and it is given by am plus 1 plus am plus 2 plus and so on. The nth term is am plus n. Okay, so this is Sn and this is Tn. Now let us prove the first part. Say this part. Suppose sigma n equal to 1 to infinity is convergent. So therefore what? Therefore, by definition, limit of its partial sum sequence, that is limit of Sn, the partial sum of this series is given by result 1. So this limit exists. Okay, this limit exists by definition. Now, if you observe this 1 and 2, from 1 we can write, from 1 we can write, say, Sm, Sm will be what? A1 plus A2 plus A3 up to Am. Okay, and Sm plus n, let us write Sm plus n is A1 plus A2 plus A3 up to Am plus n, and Sm, if you write, it is A1 plus A2 plus A3 up to Am. Okay, and if you subtract these two, what you will get is, it will start with Am plus, means if I subtract Sm plus n minus Sm, then this is equal to, all this will be cancelled, and what we are left with is Am plus 1, this term onwards. So we'll be having Am plus 1 plus Am plus 2 plus and so on plus Am plus n. Just note that the first m terms will be cancelled, and then we'll get this sum of the remaining terms from this first Sm plus n. But what is this? It is nothing but 2. So this we can write as Sm plus n minus Sm is equal to say Tn. That is the first, some of the first n terms of the second series, sigma m plus 1 to infinity. Okay. Now, from this, what I can prove here is, therefore, limit n tends to infinity of Tn is equal to limit n tends to infinity of Sm plus n minus Sm. Sm plus n minus Sm. Remember, n is tending to infinity, m is fixed, m is a fixed natural number. So this is equal to S and minus Sm. So this Sm remains as it is. Okay, because Sm is a fixed real number. It is fixed. So S is a real number because of the series sigma n is convergent. This limit exists. So it is a finite real number. Sm is also a real number. So finally, this thing is some finite real number. So what does it mean? It means limit of Tn exists, and therefore the corresponding series whose partial sum is Tn is convergent. What is Tn? Tn is the partial sum of this m plus 1 to infinity. So I can say, therefore, sigma m plus 1 to infinity an is convergent. Okay, so one way it is proved. Now let us prove the converse part. What is the converse part? In converse part, we suppose sigma say an is equal to m plus 1 to infinity is convergent. Now this is convergent, therefore the limit of its partial sum, which is given by Tn as we have defined earlier, that is equal to some finite real number. So therefore, limit n tends to infinity of Tn, this exists. This limit exists because of that result number 2, which we have mentioned here. What is 2? Let me show you. This Tn is the sum of the first n terms of this series sigma m plus 1 to infinity an. So if this is convergent, that means limit of Tn exists and it is some real number, and that real number we are calling here as T. We want to prove that the series sigma n is equal to 1 to infinity is convergent in this case. Okay, for that you should consider some of the first n terms, that is the partial sum sequence as follows. We have Sn is equal to a1 plus a2 plus a3 and so on up to an. Okay, this I can write as a1 plus a2 plus a3 and so on. Suppose m is somewhere here. Okay, plus am plus 1 plus am plus 2 up to an. So suppose the mth term is somewhere here, then the first m terms I am writing separately. And what is this sum of the first m terms? This we can write as Sm. Okay, so it is some fixed number, some of the first few terms. It is some finite number. Plus this am plus 1 plus am plus 2, which are total n minus m number of terms, and that we can express in terms of Tn. See, this is the formula for Tn. Tn is equal to am plus 1, am plus 2 up to am plus n. So it is actually Tn minus m. If I put n is equal to, m is fixed. If I put n is equal to n minus m, then this gives me am plus 1, am plus 2 up to an. So let me write this way. This is nothing but say Tn minus m, because Tn is am plus 1 plus am plus 2 up to am plus n. So putting n is equal to n minus m. Okay, so we have proved that this Sn is given by this constant. This is a constant, and plus Tn minus m, which depends on n for every n. Okay, so therefore the limit of this, limit of Sn as n tends to infinity, we can write as limit n tends to infinity of say Sm plus Tn minus m. Okay, Sm is constant, limit of constant sequence is the same number, and this is nothing but number t, because as n tends to infinity, limit of Tn is equal to t, that is given in this part. So this is finally some real number, a finite real number. So what is proved? The limit of Sn exists, and if limit of Sn exists, that means sigma n is convergent. So therefore our conclusion is, therefore sigma n 1 to infinity is convergent. Okay, so we have proved that if you add or subtract, add or remove some number of terms, some finite number of terms from a given series, then the convergence remains unaffected. So if a given series sigma n is convergent, it remains convergent. If it is divergent, it remains divergent if you add or remove some finite number of terms. Okay, so this is also very useful result, and that we are going to use in our some theorems later on. Okay, so thank you.